Okay, so we are on to the second part. This first part was painfully long. We're into the 5th week of school, technically. 5 weeks. 1 chapter of the book is done. At this rate, we'll never make it. So we will obviously be moving a little quicker now. But that's okay. We had some labs in there. We had to learn about safety. We had to learn how to write the lab, all parts that are not like curriculum in terms of information to give you. So chapter 2 talks about chemical bonding. Things will move a little quicker. This is going to be now about 2 weeks till our next test, all right? And then they'll come approximately every 2 weeks. So the first one really had this drag-on effect, a bunch of little tiny things, atomic notation and then radioisotopes and Bohr model and all that stuff. That's why I stuck a quiz in there so that we could have a little bit of a break-up and then, and then the test. So now tests will be coming about every 2 weeks. Okay, so what are we talking about now? Up to this point, we've talked about the periodic table. We've talked about atoms, how we perceive the atom, electrons, protons, neutrons. We talked about properties each of those atoms have, difference in their electrostatic force, which results in a difference in their electron affinity and ionization energy. And so now we can compare them. Which ones pull strong, which ones don't pull as hard. And that's very important. So now that we have this idea of the ability of atoms to pull on electrons, we can now talk about what happens when we bring those atoms together. Let's bring 2 atoms together, let them interact by their electrostatic force, and then let's observe what takes place. What happens to the electrons? So this next section talks about chemical bonding and compounds, just by themselves. Let's bring some atoms together and talk about the way they exist as compounds. The third part of this first unit, technically, brings 2 compounds together in a chemical reaction. So then we have reactants and products and balancing and what happens when different chemicals come together. So it's a 3-step process. Atoms in part 1, compounds in part 2, and then bring the compounds together in a chemical reaction in part 3. So, chemical bonding. Let me just talk a little bit about the types of bonds that we're going to discuss in this unit. We're going to discuss 2 types of bonding: ionic bonding, which you've already seen in grade 10, and covalent or molecular bonding. You've seen that as well. Ionic bonding involves the 2 ions together, a metal and a nonmetal, and they bond and form an ionic bond. And then the covalent bonding involves 2 nonmetals and how they get together and form a bond. All right. There are other types of bonding that exist. When you bring 2 metals together, you get something called a metallic bond, which is different. We won't be talking about that in this course. And then for materials like glass and diamond and other types of, we call them covalent network solid crystals. Doesn't matter. But diamond is an example of one. Glass is. And they have a slightly different type of bonding as well. We won't be dealing with those other 2 in this course, but we do encounter them in grade 12. Okay, so let's get a few little definitions down here. And again, as we continue to transform our view of the way atoms and molecules behave. We transform it from this idea of wants a full outer shell and needs more electrons, right? We transform that view to a physical view that involves electrostatic forces, forces of attraction and repulsion, and how that then results in chemical compounds. So chemical bond. Some people from grade 10, if I say, imagine a chemical bond, you might think of a line that exists between 2 atoms. That's a bond, right? A single bond. And you think of it as a very pictorial representation. Sorry to burst your bubble, but if we could actually zoom in and look at a chemical bond like on a magic school bus of some sort, you wouldn't actually see a line. And if we could zoom into those atoms, you wouldn't like see a letter H with a line. There would be electrons and things. So we need to get out of this idea of the fact that a bond is a construct. We do use that to picture it, but it's literally an electrostatic force of attraction that holds atoms or ions together in a compound. Again, opposite charges come together, they stick together, and we have a bond. That's essentially what a chemical bond is. Let's talk about the different types of bonding we could have, and I'm going to bring the whole thing up. And that is a classic grade 10 definition, metal and a nonmetal. They transfer electrons, form an ionic bond. And you know what? That is a good thing to keep in the back of your mind, because we do ask the type of question, is this, an ionic or covalent compound? And you've got to remember, oh, that's a metal, oh, that's a nonmetal, that's ionic. Now, as we go ahead and learn about bonding, we will learn some of the more subtleties, why it's considered ionic, and we'll be learning different ways they define it, more physical ways of which it's defined, but it's always a good thing to keep in the back of your mind. What type of compound is that? Oh, it's a metal and a nonmetal, it's ionic. It's a very simple way, but there is more detail to it. We will learn more detail. Same thing with this one here. We've got a metal, a copper ion with then a sulfate ion. That's also ionic. The metal and then the polyatomic ion stuck to it. Okay? Now, I'm going to explain to you today all the information you need to know about ionic bonding. And I'm going to be able to do it in one day. It takes one day to explain ionic bonding. It's the simplest type of bonding. You've got a positive metal ion, a negative nonmetal ion. They're electrostatically attracted because they're opposite charges. They stick together. You've created an ionic compound. As easy as it gets. I can explain it easily in one day. Now then after that, for the next 3 days, starting tomorrow, we will learn how to name all of the ionic compounds. All of that good stuff you did last year, we'll do it again. We'll talk about the polyatomic ions, carbonate, sulfate. We'll add some more to them, make it a little more complex. But because there's so many different combinations in which we can put these ions together, the naming of ionic compounds is quite complex. The actual bonding is simple, one day, but the naming is complex. I need about 3 days to tell you how to do that, okay? Now, once I'm done that, so about 4 days, maybe 5, depending on how everything goes, I will then talk about molecular or covalently bonded structures. All right? And the covalent ones are the ones with these bonds. Two nonmetals joined together by covalent bonds. Terms like single bond, double bond, triple bond. You've all heard of those before. Two nonmetals held together. Don't worry necessarily about writing maybe that last example. The two examples are good. The first example here, we've got a molecular element. All right, and here we've got then obviously molecular water. Now when it comes to explaining the bonding in a molecular substance or covalent substance, I interchange those words, that's going to take me about 3 days to explain the bonding. Ionic, simple, 1 day. Opposite charges come together, they stick together, you're done. With covalent structures, you can have all kinds of different combinations of bonds to make all kinds of different molecules. So it takes me 3 days to explain the bonding for molecules. Even though there's less nonmetals, we can put them together in many different ways. So it'll take me 3 days to explain the bonding in covalent structures or molecular structures, but the naming is easy. It takes me a day to do the naming. So it's like they're opposites. Ionic compounds, explaining the bonding is as easy as it can be, but naming is fairly complex. In molecular substances, it takes me about 3 days to teach you how the bonds are formed and all that stuff. The bonding's complex, but the naming is easy. All right? You can think of it in terms of toys. There's an analogy I can come up with. Have you ever seen, and I think they might be taking them off the market. I should buy them, but I'm just too cheap to buy them. They're like about $30 for a package of these little magnets, the little round magnets. They often sell them in the little stores. I've seen them in places like, what's that Earth one where you can buy all those?
Green Earth.
Green Earth. Oh, yes. Don't ask me why I'm in a place called Green Earth. But anyway, it's Christmas. What am I going to get? What am I going to get the father-in-law? I don't know. Put that in your garden, man. Way to go. So anyway, so you're standing at Green Earth, and they've got them at the checkout. You've probably seen them. They're little cubes, but they're made up of a bunch of little spheres, and they're all little magnets. Have you ever seen them? You know what I'm talking about? Right? And you can change the shape of them a little bit, but essentially in the end, it's just a bunch of magnets sticking together. There's only a few different little things you can do with it. The reason they're getting rid of them is because little kids are popping them in their mouth and swallowing them, and then when they stick together, if they swallow 2 of them and they get into their intestines, oh yeah, it's not good. So they're likely going to come off the market. Anyway, those are like ionic compounds. You stick them together, 2 stick together, you put another one that sticks to it. They're not that exciting. Covalent compounds or molecular structures, I would, compare to Lego, right? Lego, there's all kinds of different ways and orientations you can make those pieces fit together. You can build all kinds of different structures with Lego. So Lego, you can build complex structures because you can really have a directional way in which they bond together. So it's a more complex system. You can get more compounds out of it. Okay. But for today, I'm talking ionic bonding. That last little slide was just to us to get into our minds that there are 2 different types, and we're looking for that metal, non-metal at this point. And I'm going to bring up the whole slide, and all of this stuff, whoops, too far. All of this stuff is good to write. An ionic bond occurs when a metal atom completely transfers its valence electrons to a non-metal atom. This results in oppositely charged ions, which are electrostatically attracted to each other. So they literally stick together like magnets. The same equations that explain the way those little spheres in that little toy I was talking about, the same equations that would bind them together are exactly the same as the mathematical equations that would bind the oppositely charged ions together. It's just the ions are super small, and those little magnets are just kind of small. Not very big. All right, so we're talking atomic size, and then, something that we can hold in our hand. But it's the exact same thing. Again, if you had a magic school bus, you could zoom down to and make the size of the ions become the same as those spheres, and you had the strength, you could literally manipulate those ions exactly the same as you'd manipulate the toy. They're being held together exactly the same way. We now know that the metal doesn't just give it up because it's easier to get rid of its electrons. Oh, it's easier to get rid of one. We know now that the metal ion has a low not the metal ion, but the metal atom has a low ionization energy, a weak attraction for its outer electron. The non-metal has a high electron affinity, a strong pull on a neighbor's electron. You bring them together and just by the virtue of physics and nature, the electron is attracted to the nonmetal, makes it a negative charge, the other one becomes a positive charge, and they stick together. That's simple. An ionic compound. Let me do an example of one here for you, sodium and chlorine atoms. So I have three equations here. These, you'll notice there are no dots. They are the ionic equations. And these are the exact ionic equations we would have talked about in the previous chapter. Sodium has some energy added to it, removes an electron, leaves a sodium plus ion. For chlorine, an electron is added, makes it become chloride, and some energy is given off. And this equation here explains what happens when we put these two equations together, because they actually happen simultaneously. Last chapter, we talked about them as individuals. But now what I'm saying is the electron that's given up here is the same as the electron that's being added here, because the sodium is providing the electron. In actual fact, it's just a transfer of the electron. So if I were to add these two equations up, because you can do that with chemical reactions, you can literally add them like you add algebraic expressions. If I had an x over here and an x over here, I could cancel them away. That electron is the same as that electron. An electron as a product that's being used as an electron as a reactant is going to be the same electron. You'll notice here I also have two energy terms. This is the energy that needs to go in. This is the energy that comes out as a product. If it was exactly the same amount of energy, all right, then I would have no net energy in the reaction. In other words, it would just happen, but it wouldn't get hot or cold. It's not like it would give off any heat or absorb any. But in reality, this reaction gives off a lot of energy. This energy value is much bigger than this one. This gets all used up, and we get more energy out. So when you add the final reaction, a sodium atom plus a chlorine atom with an electron transfer turns into a sodium ion plus a chloride ion, and extra energy comes out. Okay? So if you wanted to make some sodium chloride, some table salt, from just its elements, you would actually, well, it's a very dangerous situation. Number one, we don't have any chlorine gas in the building. It's dangerous. It's toxic gas. We don't want to deal with it. And also, it produces piles of energy. I used to just say, boy, I wish the YouTube would work so I could show it to you. But it does. The YouTube works now. This is great. So let me show you. YouTube. That's funny. That's funny in a non-funny way. Excellent. So in other words, our internet is down. So with the YouTube working, the internet doesn't. Oh, that's fun. That is what we would say is typical. We'll try one more time. YouTube. No go. No video for you. But it's really cool. No. If you're interested, do a YouTube of sodium and chlorine reaction, and you'll come up with a reaction, and you'll see that it's very energetic, produces lots of energy. But it doesn't. All right. Now just a little bit of a joke. That joke is on my home screen. I don't know if you ever watched it, you ever read it. But you see, once you've got the oppositely charged ions form, they clump together to form a solid. So here we go. Yeah, look at here. The guys are all the positive ions. Yeah, you know. And then here we've got the girls, the negative ions. Look at sodium here. Look at that guy. He's just, okay. Anyway, so perhaps one of you gentlemen would mind telling me just what is outside the window that you find so attractive. And it's the oppositely charged ions. Yeah, that's good stuff. Okay. Now I'm going to draw some Lewis diagrams of these things. Don't mind the formula unit thing. You can write that in a moment. So now we want to talk about the Lewis diagrams. In other words, we want the dots so that we can explain what's happening in the formation of these ionic compounds. Lewis diagrams are very useful ways of drawing chemical reactions, and that's because they allow us to see exactly what's happening with the electrons. So, once you have magnesium and oxygen down, we will draw the Lewis diagrams for magnesium and oxygen. I hope you already know how to do that. When we get going and doing examples, if you know how to do something, please go ahead of me. And if you're unsure, use a pencil, because then if you did make a mistake, you can always go back and fix it. But if you want to gain in confidence in answering questions, you should try to be just ahead of me. If you understand what you think I need, then go ahead and write it. So I need a magnesium atom to start with. Mg, how many dots? Somebody done it? Yep, 2. And I need an oxygen atom. How many dots? Yep, 6. 1, 2, 3, 4, 5, 6. We're going to put a plus in here. And in grade 9 and 10, maybe you didn't do these in grade 9, but in grade 10, right, your teacher might have said, oh, look at that. That's a match. That's a perfect match. They were meant for each other. Why is that? Why are those? Yep. Excellent. Perfect. The 2 could fill oxygen's outer orbit. And you might have even did something like this. You don't have to do this. This is grade 11. But you might have went, okay, let's draw an arrow so that we can see where it goes to pair those electrons up. Excellent. Again, you don't have to do that here. I'm just reminding you of the good old days in grade 10 when science marks came easy. Remember those good old days? Nobody's laughing. Good stuff. Too soon after the test for that. All right, so now we're going to draw our ions. We've already learned how to draw these ions because it is a Lewis diagram. I have to have square brackets. Those electrons are now over with the oxygen. What's the charge on this? A positive what? +2. +2. And oxygen, it had 6 and now gained 2 more. It's got 8, and what's its charge? Bless you. Right when it was quiet. That was fun. Yep. -2. -2. Okay. Now, I had a question in the morning class. Do we really need to put the electrons around the oxygen? It's a full outer shell, kind of like the magnesium. Do we really need those? And the answer is very much yes. All right? In a Lewis diagram, whether it be for ionic compounds or for covalent compounds, when we draw Lewis diagrams later on, we must always have a proper accounting of all of the valence electrons that we have. So how many valence electrons am I dealing with in total for my reactant atoms? How many valence electrons in total am I dealing with here? Yep, 8. 6 from this one and 2 from this one. That means in my final picture, I also have to have 8 valence electrons. You can see in this picture there's 8 around the oxygen now. Those valence electrons have been given up by the magnesium. So I also have 8 in my final picture. Excellent. If you don't have the same amount, then you've done something wrong. You've either lost or gained some electrons. Okay? When I was in high school, as you might think, my English mark was not very good. And my English teacher always, she used to say to me, she'd say, do you like own a comma salt shaker? I'm like, what are you talking about? Because this is exactly what I did. When I would write an essay for something, I would never use any commas. My sentences would run on by miles and miles. And then I'd say, I probably need some commas. Oh, there. I took a breath there. That looks cool there. And I haven't used one in a while. We'll put one there. Made absolutely no sense. So she thought I was just sprinkling them everywhere. She was right. I find, though, young chemists, when drawing Lewis diagrams, sometimes suffer from having an electron salt shaker, where when they want to finish a diagram, they kind of go, well, let's put an electron there, and there, and there. Beautiful, fabulous. Like they're some kind of an artist. Just adding electrons anywhere. Well, you can't do that, right? In a substance, the atoms that come together have so many valence electrons, in this case, 2 and 6, 8, and therefore, in the compound, it must contain the same number of valence electrons, because the electrons can't just appear from nowhere, and they can't just disappear to nowhere. They've got to come from the chemicals that are involved. All right. Now you can write down formula unit. And the text box kind of wrapped around. Formula unit is the smallest unit of an ionic compound. However you want to write that in a straight line, you can do that. When we're talking about a covalent substance like water, and we want to describe that smallest piece of water, what do we call that smallest piece of a covalent compound like water? We call it a water. We call it a molecule. That is correct. Thank you, sir. But ionic compounds are different. Ionic compounds form something called a lattice structure. We'll talk about that later. And so we can't talk about ionic molecules because they're different than water. The smallest piece of an ionic compound is called a formula unit because it's the smallest piece that represents the chemical formula for that particular substance. So in this case, the formula unit for this compound consists of 1 magnesium, Mg1, which we don't put, and 1 oxygen, 1. So the formula unit for this is MgO. Okay? Now the name. We know how to name each of these ions. When metal atoms become ions, they keep the same name. So this is magnesium. But when the nonmetals become negative ions, actually anything that's a negative ion, will have this particular name. What's it going to be? Yep. IDE, and this case it's oxide, correct. Magnesium oxide. So all we're literally doing to get the name of the compound is putting the name of the positive ion with the name of the negative ion. Magnesium oxide. Let's do a handful more of examples. So again, if your confidence is a little low, or maybe if your confidence is high, even, I have a lot of confidence, but I hate using a pen because my spelling stinks. Okay, I don't have confidence with spelling. Use a pencil. Then if you screw it up, you fix it. If you use a pen and you don't mind scribbles all over the place, then pen away. I am recording this, Bradley, so that you can watch it again at home, okay? So, magnesium. How many dots? Just tell me. 2. Chlorine. 1, 2, 3, 4, 5, 6, 7. Oh, that's not a perfect match. Ah. Those hippie grade 10 teachers that talk like that. What do I need to do to take care of this? Colt? I need 2 chlorines. All right? I'm not going to draw the arrows, but I'm going to end up with 1 magnesium ion and 2 chloride ions. To draw it officially correct, you put the one that has the lower number right in the middle so that you're flanking it with two chlorides, all right? But you don't have to. If you were to put a magnesium and a chloride, that'd be fine with me. I don't care about the order. But the proper way to do it would be to put the magnesium in the middle, +2, and then 2 chlorides on the outside, right, -1, and then 1 over here, -1. Again, each of those electrons went into making a chloride ion. Again, we can check whether our valence electrons are correct. How many valence electrons do I have in total in my starting atoms? How many valence electrons? Just total them up. What is it? Yep. 9. Nope. Yep, that's okay. Forget it. That extra 7 just threw you right over the bend. You had 9. Now you just need an extra 7. 16? I'm going to take that you said 16. Excellent. 16. We're going to build that confidence, Jess. We're going to build it. Okay, 16. 16. How many do we have on the right? 16, right? So we're okay. We're good. All right? Because we had 2 chlorine atoms. So that's a good structure. Formula unit. Please don't be offended by my short form. Formula unit. That's what it means. What's the formula unit for this one? Yeah, cool. Yeah, NgCl2. The formula unit, folks, is essentially what we also call the chemical formula, right? I'll talk again why it's called a formula unit in a little bit. Excellent. Name of this one. Sorry? Magnesium chloride. Magnesium chloride. Okay? All right? 2 more examples. And I'll have you write them down. You now should kind of know how long or how much space to leave. So lithium and nitrogen, you can write that down. Then leave some space, and I'll go to the next slide as well, and I'll put that one down. I'll let you guys have a little bit of time to work on it, and we'll take them up in a moment. So lithium and nitrogen, first pair. And the last one we'll do is aluminum and oxygen. So I'm going to just go back to the lithium and nitrogen slide. Again, you guys have your own periodic tables, but if you want to squint at the one at the front, sure, squint away. And don't be afraid to add as many atoms as you need in order to make sure everything ends up happy in the end. And what I mean by happy is neutral. In the end, that aggregate of ions that you make has to be neutral in the end. Trading electrons back and forth so that everything has been paired up and traded over. Also, another check is that the amount of valence electrons you add at the beginning is the same as the valence electrons you have in your compound at the end. No magically appearing electrons or disappearing electrons. It's against the law of conservation of lots of stuff. Charge, mass. Okay, we've got to be getting close, I would think. Lithium, how many dots? 1? Yep. Nitrogen? Yeah, you just blurt it out. We don't have to. Yeah, 5. 5's good. 1, 2, 3, 4, 5. All right, now maybe with a hand up. What do I need to do to solve this problem? What do I need to do? Yep, it's. I need 2 more for a total of 3. So I'm going to just put 3 in front of that one, right? We don't need the arrows. We get the idea. Now we're going to have 3 ions of lithium and 1 ion of nitrogen. And I would put the nitrogen in the middle with the lithium kind of around it, right? It doesn't have to be. If I'm asking you this on a test and you just put nitrogen with the -3 and then 3 lithiums, fabulous, right? Really, it's not a true representation of what the ionic compound looks like. It's just distributing the charges, all right? So I'm going to put the nitrogen in the middle. And what do I need around that guy? Again, 8 electrons. That's what I'm looking for. 1, 2, 3, 4, 5, 6, 7, 8. And that charge is -3. And then I've got 3 lithiums that have no electrons. It's given it up, and it's +1 lithium. And again, whether you put it around nicely, I'm not that concerned. Lithium +1. So overall, it's neutral, all right? And 8 electrons to begin with, 8 electrons at the end. We're in good shape, okay? And now aluminum and oxygen. Al, how many dots? You can just tell me that one. 3. Oxygen, 6. We've seen that guy. And now maybe again with a hand up, how am I going to solve this problem? Again, I've got to have everything neutral in the end. I got to have proper number of electrons. How are we going to deal with this? Riley? Yeah, 2 aluminum and 3 oxygen. And you're going to find in chemistry, because we always balance things, right? Chemistry is very much one of these things where we're balancing equations or we're balancing electrons. And when you get that situation where you've got 3 of something and 2 of the other, you're always thinking a common factor of 6 and just switch the numbers over so that everything becomes 6. So if I've got 3 electrons and I need 6, then I need 2 of those things to make 6 electrons. And here I've got 2 spaces and I need 6 spaces. 3 of those will make 6 spaces. So that 2-3 crossover thing shows up over and over again. We'll see that in the near future, especially tomorrow when we get starting about naming things. Okay, so again, this becomes a little ugly. We've got ions everywhere. We've got less aluminums and more oxygens. You know what, I'm really not that concerned. Let's just start drawing them up. Aluminum, what's its charge going to be? Somebody just have it? I don't need a hand up on that one. Yep, +3. +3. Let's put an oxygen next. And what's the oxygen charge going to be? No hand up for this. -2, because it's gained 2. And now I'm going to have enough of all of them, right? So let's just go with, we'll put another aluminum down here to make 2. It doesn't make any difference. We'll put another oxygen down here. -2, and I need a third oxygen. I'll just put it over here. -2. Overall negative charge is -6. Overall positive charge is +6. How many electrons did I have in total? 6 and, oh goodness, what is this? This is 6 times 3, that's 18. 18 plus 6. What did I do? 24? 24 electrons? Have I got 24 electrons in here? 8 times 3, 24. All right, good. We've accounted for all of our electrons. Formula unit. Essentially the formula that comes from this. What are we going to get? Cindy, what do you got? Al2O3. And the name? Aluminum oxide. And I have to say it like that because of all the N's and the M's, and I would spell it horrifically wrong if I didn't say it like that. Okay. Let's now talk about ionic crystals. Don't write down the recall. I used to do this lesson in a slightly different order, and so sometimes I had to end at that spot and I would start again the next day, and I would have to tell people to recall the formula unit. But we just wrote down a bunch of formula units. Due to the fact that the formula units of an ionic compound has a positive end and a negative end, other units will be attracted and form a continuous 3D lattice structure of repeating ions. What a great scientific paragraph. All kinds of cool words in that one. Essentially, what does it mean? Because we have opposite charges in an ionic compound, the ions will clump together. They will clump together with repeating positive, negative, positive, negative, positive, negative. And that clumping together forms what we call a lattice structure. All right? Now I'm going to flip the slide here in a minute. There's pictures on the next slide. Don't write it down. I'm going to show you what I want you to write down, a very simplistic way of representing a lattice structure. But let me then explain in detail what we mean by a lattice structure. So, three-dimensional lattice structure of positive and negative units. Here is a little microscope picture of sodium chloride, salt itself, all right? Table salt. And when the chloride and sodiums get together, because of their size, they will order themselves in this fashion. Chlorine with a sodium beside it, flanked by another chlorine with another sodium and a chlorine and a sodium. And that structure continues and continues and continues. So in a salt crystal, there isn't a whole bunch of little NaCl's, but there's a bunch of individual Na pluses and Cl minuses. That's why we can't call a sodium chloride piece a molecule. A molecule itself has a beginning and an end. It has a defined structure, 2 H's and 1 O. That's a water molecule. But an ionic compound doesn't really have a beginning and an end. You could say, there's one sodium chloride, or there's one, but you could just argue as much that that's one, or even that's one. So we can't say where the sodium chloride piece begins and ends because it's repeating over and over again. But what we can say is that the simplest representation of the ratio of sodium to chlorides is 1 sodium to 1 chloride. Hence we call it a formula unit. All right? Now, these things will automatically clump together and form this great structure. And it's actually three-dimensional. Here we've got one surface of that repeating structure, but then notice in behind it there's another layer that's just moved over by one ion. So I could cut this in whichever direction I would like, and I would get that same representation. I would get that lattice structure. A lattice is simply a word that represents a repeating structure. If you go to the lumber store and you're building a deck, and you've got a hot tub in your backyard, and you don't want the neighbors looking, in your backyard, you buy lattice. What is lattice? What are we talking about for lattice? Not right now, all right? I'm in the middle of something, okay? So what am I talking about if you go to the lumber store and you buy a piece of lattice? You guys know, you guys, yep. Yeah, pieces of wood that are kind of going this way and then going this way, right? So then you'd have to really be a weirdo looking in the hole, right? If you really wanted to get a look, because you can't see through the lattice, but it lets some air through. It's a repeating structure. That's why they call it lattice, all right? Scaffolding is also lattice. Do you know what scaffolding is? Do you know what scaffolding is? It's a construction platform that they put on the outside of a building so that the workers can work on the building, and it's made of pipes and that type of thing. There's always some of it on the outside of the playhouse. I don't know why. They're always fixing that building. But that's what scaffolding is. Again, repeating structures. And scaffolding is very strong because one piece supports the next piece so that it can't fall over. That's the same thing with a crystal lattice, except it's on an atomic scale. A small, tiny little lattice structure where the positive ions are attracting to keep it together, but they're also preventing it from moving over. So an ionic crystal is super strong, all right, because they hold each other up, all right? If you take a piece of salt, you can't just squish it with your thumb. Like if salt ends up on the table, even if you have like a big piece of sea salt, you can't just squish a piece of salt like you can squish a bit of butter that ended up on the desktop. Let's say you're making some bread, and you got butter all over the place. If you push the butter with your thumb, spreads out, right? It might even sound like that. But if you do that with a salt crystal, it doesn't work. You can crush a piece of salt, maybe with the back of a spoon, and you could get it to cataclysmically fracture, but you're never going to get it to squish. And that's because the ions are making this scaffold structure that is resisting your pressure. If you push hard enough, you'll break that ionic crystal structure and it'll shatter and break. Scaffolding can come down too on a building. If it's not supported right and the wind blows hard enough, you could get the scaffolding to come down. All right? Let me just show you a couple of things that I need you to do. Number one, let me draw a representation of what I want you to write as a crystal lattice. You can put this under your note. So all I want you to put in here is Na plus, Cl minus, Na plus, Cl minus. We're getting the idea that it's repeating. I'm going to do one more. I'm going to do 2 more layers. What do I have to have this time? Cl minus, Na plus, Cl minus, Na plus, and we'll do one more just to get the idea that it's repeating, Na plus, Cl minus, Na plus, Cl minus. A lattice structure. That's just two-dimensional, but there would be another layer on top. It would go on and on and on depending on how big the crystal is. Okay? All right? One last, well, no, not last. One other thing I want to show you, and I didn't get a chance to show this morning's class because I forgot I had it. Let me just show you this neat little program here, right here. This little program is called Interactive Physics, and it's a fairly old program, and I used to use it when I taught physics, but it's also neat in simulating some simple chemistry things. In this virtual beaker, in this virtual container, there are red and blue ions. And the red ones are positive, and the blue ones are negative. You'll notice they're separated out right now. In a program like this, we can program physical properties for these ions. What we've programmed for them now are opposite charges. What I'm showing you here is, if you have a bunch of oppositely charged particles like ions together that can interact with each other, something just naturally happens due to the laws of physics. So if I run this simulation, we can see them bouncing around. Those arrows represent forces that they're feeling. And in the end, notice what happens in the simulation. What happened? What did those ions automatically do on their own without any outside help, just by virtue of their opposite charges? Yep. They formed a lattice structure. That's a perfect answer. I was hoping clumping together, but wow, lattice structure is fabulous. Even this group is still feeling an attractive force on that group, and will also join the group in the end, and we will have created a lattice structure. So oppositely charged objects automatically simply clump together to form these ionic crystals. All right? Let's reset. Neat thing about simulations is I can change things. I can go with interaction strength. Let's turn it up. We'll turn the strength up a little bit. That means they're attracted even more. Well, that didn't do much different. They did come together in a different orientation. They're having difficulty kind of getting together, but oh, there we go. There we got it. That's not bad. Look at it. It's actually a different shaped crystal. Thank you. Notice now, I've got this funny alternating pattern with this alternating pattern here. So just by changing the strength of the force, I've now created a different crystal structure. And there are many different crystals that exist depending on how strong those ionic interactions are. So that's kind of a fun little program. Question, oh, I'm going to close it up. Did you want me to do something? Oh, test back. 44. Yes, I need to get a couple of other things done, but yes, test back will happen. Let me just advance you. I need you to write that one. You don't need 15 minutes for test observation. No. So ionic compounds have a lattice structure of oppositely charged ions supporting each other, holding each other together, keeping each other in a very strict lattice form. And it's a very strong structure, like scaffolding. These structures predict many properties of ionic substances. Number one, they're electrically neutral. The negative charges always balance out the positive charges. So an ionic crystal is neutral. They're hard. They're hard crystalline solids. They form crystals. That's because of that lattice structure. Very strong, very stable. You cannot squish a piece of salt with your thumb on a tabletop. They have high melting points. It takes a lot of thermal energy to get those ions to wiggle out of their crystal structure. And that's essentially what melting is. Solids have their pieces, in this case ions, in a regular ordered state. Right now, if I were to describe you as the class in the way you're sitting in rows, I would describe you as being in the solid state. You're all in a spot. When melting happens, the particles are able to move out of those spots, kind of like when the bell goes. The bell is like a Bunsen burner. It gives you energy. Gotta go to the next class. You all get up and start moving, start flowing. So as students move down the hall in different directions, there's no order whatsoever. Some chaotic flowing. That's the liquid state. So right now, in class, solid state students. I love them the best. They just sit there. The bell goes, you start to flow. Liquid state. In order to melt an ionic compound, you've got to get that nice lattice structure to let those ions start to move around. They've got to break away from each other. It takes a lot of energy to do that because they're really held together tightly. Solid at room temperature. Do not conduct electricity in the solid state. I have to talk about what conducting means, but they're non-conductive. I'll talk about that maybe tomorrow. They're brittle. When you push on them, they don't squish, but if you push on them hard enough, they'll fracture and break cataclysmically. A cataclysmic break. They do not conduct electricity in the molten state. Oh, sorry, they do conduct electricity in the molten state, melted state, and in solution due to the formation of ions. Now, normally I would now talk about what it means to conduct. Actually, I still am. I don't think you need 10 minutes. I'm going to put one more slide up, maybe two. I have to talk a little bit about electrical conductivity, because that is the main way we tell the difference between an ionic substance and a covalently or molecularly bonded substance. I need to slightly amend your view of electricity or electrical conductivity. In grade 9, you learn that electricity is the flow of electrons through a wire. And if a substance conducts electricity, it allows the electrons to flow. That's what you learn in grade 9. And everything is about the electrons. It turns out that that's a specific example of electrical conductivity. it's not the electrons themselves that is conducting the electricity, but it's the charges that they have. So more specifically, actually more generally, it's not that electrons need to flow, it's just that charges need to flow. Ionic compounds have charges in them. And if those charges are locked in place in the lattice structure, electricity can't flow. But if the charges are able to move and flow along, positive charges one way, maybe negative charges the other way, that's the flow of electricity. That is conducting. So it doesn't have to be electrons that flow. It just has to be charges that flow. So I've got one more slide. I actually got two, but I'm going to do one more, which talks about why, when we dissolve an ionic compound, why does that allow electricity to flow? Are we good to go? We got Zach just finishing off a few lines there. You got it? Okay. And this is going to involve a little diagram in that space. I had a little animation there, but the new PowerPoint program doesn't allow my animations anymore. In solution, when dissolved in water, ionic compounds will form mobile ions which conduct electricity. We call this solution that can conduct electricity electrolytes. It forms what we call an electrolyte. I had someone in the first period say, is that like in Gatorade? It's got electrolytes. And it is. It's exactly the same. In Gatorade, there are ionic compounds that your body needs in order for your nerves to send electrical impulses and therefore be a better hockey player. I don't know. Whatever the Gatorade pretends that you become when you do that. So they contain ionic compounds. Let me draw a little picture representing this. So here I've got a beaker, here I've got some water in it. And here I've got a little bit of Na plus, Cl minus, Na plus. You get the idea. That's my salt. I'm going to put one more layer. Cl minus, Na plus, Cl minus. And when it dissolves, some of the Cl's end up moving around in the water, and some of the Na's end up moving around in the water. That's what dissolving is. The ions are set free of their lattice and are able to move. So they're moving around. If I put an electrical conductivity apparatus in the water, and one has a negative charge and the other has a positive charge, then the sodium will move to the negative and the chloride will move to the positive. And if I have a power supply and a nice light bulb on there, then that light bulb is going to light up and I have an electrolyte. All right? The ions become mobile. There are some homework problems. Some. These are more check for understanding. You get to them when, before you get to the test and you have a good understanding of it, and they've served their purpose. So do I have to have them done for tonight? Am I going to check the homework? Well, you know the answer to that. Do you want to look at these before we have a test in the next 2 weeks? I'd say yes. Okay, test's coming back. The multiple choice was only out of 29 instead of out of 30 because we didn't do number 24. Remember, we couldn't do that one. Emma. Christy. Jenna. Barb. Don't know how many Jennas I got. I got so many Jennas in my other classes. Riley. Jocelyn. Wes L. Cameron. Zach. Justine. Right there, right there. Rachel. Oh, Rachel I. Guys, you get to keep those. Yep. Justin. Marcy. Wes. M. Jordan. Braden. Josh. Oh, Marcy right there. There you go. Braden right there. Josh in my hand. Cindy. Marika. Sophia. Carissa. Dave. Cole. Lily. Nathan. Lily, Nathan, Miranda, and Michaela. Again, I will be posting the answers on the board. I got up Mark. Bradley's right here. All right. Oh, am I still recording? I am. Don't need all that stuff on the thing, do I? I stopped my recording.